Hey guys, welcome to homework number 10. It's going to be a kind of different setup today. I don't have my TV. So what I'll be doing, I'm recording over Zoom. So I'll be sharing the problems and at the same time solving them. So I'll just share the problem, I'll stop sharing, and then I'll start solving. And don't get worried that I have been painting my house, so my hands are white. I'm going back to paint after this. So I'm not trying to bleach and become white. I'm still the same black guy, So it's okay. I'm going to start sharing right now. Let me see if I have this pulled up. Okay. Okay. I want to believe you guys can see this. So this is the first problem. An object is oscillating in simple harmonic motion. Focus on concept question 4. With an amplitude A and an angular frequency omega. What should you do to increase the maximum speed of the motion? So let's see how omega and maximum speed are related. V is omega A, okay? So omega times amplitude is your V maximum speed, okay? So that is very important. So increase A by 10%, reduce omega by 10%. No, those just counter each other. So you have to increase both A and W or omega by 10%. So the correct answer is C for that one. Then the next problem says, focus on concept question 06. An object in simple harmonic motion has an amplitude of that and an oscillation period of that. Determine the maximum speed of the motion, okay? So we are given the amplitude and the period of oscillation, and we are asked to find the maximum speed. So I'm going to write this down. So amplitude is given to be 0.352 meters, and the period t is given us 0.62 seconds. Okay, so I'm asked to find Vmax. So I will stop this so I can solve this problem for you guys. So I'll stop sharing so you guys can see me clearly. Okay, now. So Vmax is omega A. So we have A, but we don't have omega. We have T, the period. T is 1 over frequency. Is that okay? And I know frequency, 2 pi frequency is omega. So what is frequency? Is omega over 2 pi. So period is 1 over frequency. So period is 1 over omega over 2 pi. So it's just 2 pi over omega. So what is omega? 2 pi over period. So it's just 2 pi over 0.62. Okay. 2 pi over 0.62. Have my calculator right here. So I do that, 2 pi over 0.62. .1355. So my omega is 10.1355 radians per second. And I have my A amplitude 0.352 meters. So what's my Vmax? Omega times A. So this times that, 10.1355 times 0.352. And what does that give us? .1355 times 0.352. 3.57. So we have 3.57 meters per second. Let's make sure that is what they have there. So I go back to share. 3.6 meters per second, approximately. So that's correct. So let's go to the next problem. And the next problem, focus on concept question 07 says, the drawing shows a graph of displacement versus time for simple harmonic motion of an object on a horizontal spring. Which one of the following answers correctly gives the magnitude v of the velocity and the magnitude a of the acceleration at point A and B in the graph? Is that okay? So you start, you go through point A, and then you go back to point B. Is that okay? So this is the starting point, and you go like that. So at this point, this is when you extend the spring out, if it's a spring on a mass. So when you let go, it comes, this is the equilibrium position, it goes back and forth like this. So from here you drag, it goes opposite, goes, so like this. So it's going back and forth. So the speed is maximum in this whole point, anything here. The speed is 0 here, but it has the maximum acceleration here, anywhere here. So A max, V0, V max, A0. Okay? So it said velocity A is maximum at A, so this is point A, and this is point B. If you like, point A, point B. So all these points are point A, all the points on top are point B. Okay? So it says A is 0, AA is 0, that's correct. VA is V max, correct. For A, VB is 0, correct. AA is maximum. Is that okay? So that's wrong. So the correct answer is A, okay? The correct answer is A. So the other ones are wrong, okay? So the correct answer is A in the problem there. So VA is maximum, AA is 0, VB is 0, AB is maximum, okay? Next problem. So it says a hand exerciser utilizes a coiled spring. A force of that is required to compress the spring by that. Determine the force needed to compress the spring by 0.0578. So the first thing to do here is to get the constant, the spring constant. So we need the spring constant, okay? Let me see if I can zoom in this a little bit so you guys can see me better. Okay. So I'll wipe this off. So in this problem, I'm going to write down the parameters. 87.3 newtons, cost an extension 1, x1 of 0.0238 meters. So they're asking me to find the force needed to compress by, so I'm looking for F2 to compress by 0.0578 meters, okay? So I'm stop sharing so you see what I'm solving. So I'm going to use F1 equals kx1 from Hooke's law. To get k, it doesn't matter which f and x, so k is F1 over x1, 87.3 over 0.0238, that gives me k. So I do that really quick. .3 divided by 0.0238. $3668.07. 3668.07 Newton per meter. So that is my spring constant. So now, if I apply a different force for this extension, what's this force? So F2 is K X2, the same K that I got, 3668.07 times X2, 0.0578. So what does that give me? $212. So let's check our answer and make sure we are right. We get 212. So I'm going to share that. 212 newtons, exactly, 212 newtons. So that's the force. So use F1 and X1 to get K, then put K in F2 and X2. You get F2. That's done. The next problem says, chapter 10, problem 02. The drawing shows 3 identical springs hanging from the ceiling. Nothing is attached to the first spring, whereas a 4.1 Newton block hangs from the second spring. A block of unknown weight hangs from the third spring. From the drawing, determine the spin constant and the weight of the block. Okay, so we can get the spin constant from the second spring. Let's get the extension. So 20 is when it was extended in centimeters, then it extended to 35. So the extension X becomes your extension X is 35 minus 20, 15 centimeters, 0.15 meters, okay? 0.15 meters. That's your extension. And then that extension was caused by a force of 4.1 Newton. So F is 4.1 Newton. So this F1, X1. So let's get K. F1 equals KX1, okay? So we're asked to find the other weight that goes to, for the B part, 50. So X2 is 50 minus 20, 30 centimeters, 0.3 meters, okay? Okay, now let me go back to the problem. So I stop sharing. Okay, so the A part asks us to get the spring constant if this weight elongates it from 20 to 35. So F1 equals KX1. So K is F1 over X1. That is 4.1 over 0.15. So what does that give me? 4.1 over 0.15. I do that really quick. $27.33 Newton per meter. So that's the correct answer. Now, a force elongated to 50 centimeters. So that force F2 is KX2. We've already gotten our K, so the 7.33 times 0.3. So we do that, 27.33 times 0.3, 8.2 newtons, exactly. That's the force that will do that elongation for the second part. Okay. So let's go to the next problem. I'm going to share the problem again now. Yes, 8.2 and 27.33, correct. So chapter 10, problem 15 says, when responding to sound, the human eardrum vibrates about its equilibrium position. Suppose an eardrum is vibrating with an amplitude of that. So I'm going to write down my variables really quick before I stop sharing so you guys can see the solution. So I'm going to put down the parameters I'm given in the problem. So I have my amplitude giving us 4.6 times 10 to the 7, 4.6 times 10 to the negative 7 meters. Maximum speed 3.3 times 10 to the power minus 3. V max is 3.3 10 to the power minus 3 meters per second. Frequency, what is the frequency in hertz of the eardrum's vibration? So we're looking for F frequency. So we're asked to find F and maximum acceleration. We also aim to find A max. Okay. So now let's stop sharing and solve the problem, okay? Good. So, this is my amplitude given to me. Oh, it looks like this is cutting off a little bit. So let me zoom out a little so you guys can see. Or let me just go this way a little bit. Yep. And then zoom back in. Okay. Now, I'm giving A and V max. I'm asked to find frequency. That's easy because I can get omega. Omega A is V max. So omega is V max over A, so which is 3.3 times 10 to the power negative 3 over 4.6 times 10 to the power negative 7. So that'll give me 3.3 over 4.6. 3.3 divided by 4.6. 7.17 times 10 to the power 3. 7 minus 3 is 4. 3. Because I brought it in once. So 7.17 times 10 to the power 3 radians per second. That's my omega. But I'm on my frequency F. 2 pi frequency is omega. So omega is frequency is omega over 2 pi. 7.17 times 10 to the 3 over 2 pi. And what does that give me? $141.62. 141.62 hertz. So let me check that answer first and make sure it's correct. So let me check the answer they have here. Let me share back the screen. 141.62. Yeah, 141.8. So about, is it 141 or 1141? Let me make sure, sorry. 1141, sorry. 1141 point, yeah. So about that, little difference. So what is the acceleration of the eardrum? So they got 23.7 meters per second squared. So let me see if we get that for the acceleration. So we know V max is omega times amplitude. A max is omega squared amplitude, okay? So we square omega, okay? Omega is given, where is it? Right here. 7.17 times 10 to the 3 squared times 4.6 times 10 to the power negative 7. Okay, so we do that really quick and see what that gives us. Okay, and see what that gives us. So 7.17 squared times 4.6 . So this gives me 23.7. 23.7 meters per second squared. So let's check the answer. I think that's about right, what they got right here. 23.7 meters per second squared. Yep, correct, 23.7. So let's go to the next problem. Chapter 10, problem 18. A 0.98 kilogram object is attached to one end of a spring, as in the first drawing, and the system is set into simple harmonic motion. The displacement x of the object as a function of time is shown in the second drawing. With the aid of this data, determine the amplitude of motion, the angular frequency, the spring constant. So let's draw into the next. Good. So this is the next slide. So that's the drawing. So determine the amplitude. So the amplitude is the maximum vertical displacement, as you can see there. So the amplitude will just be 0.08 meters. So that's the correct answer for A. Number 2 says, the B part says the angular frequency, omega. So let's see the period. The time for one oscillation is 4 seconds. So it took 4 seconds for one complete oscillation. So T is 4. So I'm going to do that right here. So your period T is 4 seconds. So T is 2 pi over omega. Is that okay? Because omega is 2 pi frequency, which is 2 pi over T. So T is 2 pi over omega, okay? So what is omega? 2 pi over T. That's 2 pi over 4 seconds. That's pi over 2. So that's 3.142 divided by 2 for omega. 1.57, 1.6 radians per second. Correct. So omega is just 1.6 radians per second. That's the correct answer for B. The C, the spring constant, K. So omega is the same as square root of K over M. So K is omega squared M. Is that okay? Is that okay? So let's do that. Omega squared M, so we have the mass 0.98 times 1.6 squared. 2.4 newtons per meters, correct. Correct answer. So this is C, this is B. So D, the speed of the object at t equals 1 second. So remember, at t equals 1 second, okay? So what is the speed there? First of all, the slope there is 0, so the speed there is going to be 0. So you have 0 speed there at that top, remember? So the speed there is 0 because it has no slope. And then the E part says the magnitude of the object acceleration at t equals 1 second. So at t equals 1 second, that's when you have A max, your maximum acceleration, which is omega squared times amplitude. So your A max is omega squared A. We know our omega, 1.6 squared times amplitude 0.08. So let's do that. .2 meters per second squared. Correct. So that is the answer for E. And D, the velocity is 0 at that point, okay? 0 at that point. So I hope you guys can see the calculation. Sorry, I forgot to stop sharing for you guys to see. So the period is 4 seconds for one oscillation. It goes like that. 2, 3, 4 seconds, okay, for one oscillation. So 2 pi over omega is your period. So omega is 2 pi over period. So we got omega to be 1.6 radians per second. Then that was B. C, omega is square root of k over m. So k is omega squared m. So we square 1.6 times the mass. And then give us this guy. And then D, V0 at that point, A max is omega squared A. You square omega squared times the amplitude, and then you're done. So amplitude is the maximum vertical displacement for the A part, 0.08. Okay, next question. So I'll start sharing again for the next problem. Chapter 10, problem 21. A spring stretches by 0.0152 when a 2.5 kilogram object is suspended from its end. How much mass should be attached to this spring so that its frequency of vibration is 7.06 hertz? Is that okay? So this is simple. Get the spring constant, and then we can get the mass from that frequency. So I'm going to do that here. So F equals Kx so the force is the weight, 2.51 times 9.8 equals K times, because it's suspended, so it's when it's hanging from its end, 0.0152. What is K? Is 2.51 times 9.8 divided by 0.015. Let me see if I have a marker that writes better. Okay. Check right here. So let me stop sharing so you can see what I'm doing. Okay. So K becomes 2.51 times 9.8 divided by 0.0152. 1618.2895. 1618.2895 Newton per liter. So this is K. So they're asking us to find the mass that will give it a frequency of 7.06 hertz. So we know 2 pi frequency is omega, and omega is square root of K over M. So we already have K, so we can find the mass that will give this frequency. So that's all. That's how you do the problem. So omega is 2 times 3.142 pi times 7.06. That gives you your omega. So let's get that first. (44.37 radians per second). So that's omega. So if that's my omega, That is the same thing as square root of K over M. So that omega is the same thing as square root of K over M. So 44.37 equals square root of K over M. So M becomes 44.37 squared. So K divided by that. That's all. So K, we got to be 1618.2895 divided by 44.37 squared. So we do that. 1618.2895 0.822. 0.822 kilograms. That's all we have. Let's check the answer and make sure we are getting the right thing, okay? 0.822 kilograms exactly. That's what we have here. So next question, chapter 10, problem 37 says a spring is compressed by that and is used to launch an object horizontally with the speed of that. If the object were attached to the spring, at what angular frequency would it oscillate? So we have the V and omega. So this is just simple. V is omega A. So it's stretched to the amplitude. So omega is V over A, which is 2.75 divided by 0.0867. That's all. So let's do that. Make sure we get the right answer. 2.75 divided by 0.0867. 31.7, exactly. 31.7 radians per second. So next problem says, 5 simple pendulums are shown in the drawing. The length of the pendulums are drawn to scale, and the masses are either M or 2M as shown. Which one has the smaller angular frequency of oscillation? Okay. So what is the angular frequency? The angular frequency depends on the what? The length. Remember? 2 pi root L over G is your period. And this is the same thing as 2 pi over omega. Okay? So it doesn't depend on the mass. It only depends on the length. Okay? So which one has the smallest angular frequency? So let's go. So omega will go as, let me come out here. Let me stop sharing so you guys can see what I'm doing. So I'll come right here. For a simple pendulum, 2 pi root L over G is your period, and period is 2 pi over omega. So it means your frequency is inverse of that. It's 1 over 2 pi root G over L. So this is omega over 2 pi. So your omega go as G over L. Is that okay? So omega is proportional to square root of G over L. It has nothing to do with the mass. So the one that has the smaller L, we have the larger omega. The one with the larger L, we have the smaller omega. So that's all. So smaller L has smaller omega, larger L, smaller L has larger omega, and smaller L has larger omega, and larger L has smaller omega. So which of them has the smallest omega? It will be the one with the largest L, so which is B. It doesn't matter what mass it is, okay? So let's share the screen and see that. So B is the one with the longest length that will have the smallest omega according to that inverse variation. Next problem. The period of a simple pendulum is that the length of the pendulum is doubled. What's the period of the longer pendulum? So you double the length. What happens to the period? So you have 3.1 seconds. Period is 2 pi root L over G. So 3.1 seconds is for one length. So let's get that length and then double it. So let's stop sharing. So 3.1 equals 2 pi root L over 9.8. So L equals 3.1 squared times 9.8 divided by 4 pi squared. Okay. So what does that give you for the length? So this length is 3.1 squared times 9.8 divided by 4 divided by 3.142 squared. 2.385 meters. So now let's double this length times 2. 4.77 meters. So this 4.77 meters divided by 9.8 square root of L over G 2 pi equals what period? So when I double the length, what period do I get? So let's do that. Divided by 9.8 square root of that times 2 pi. 4.38 seconds. So let's check if that's the answer. 4.38 seconds. So we get 4.38 seconds. So let's check if that is the answer right here. So I'm going to share again. 4.4 seconds, correct. The next problem, chapter 10, problem 27 says, a spring is hung from the ceiling. A 0.596 kilogram block is then attached to the free end of the spring. When released from rest, the block drops that before momentarily coming to rest, after which it moves back upward to oscillating. What is the spring constant? This problem, the first way is to do the conservation of energy. So half mv final squared plus mgh final plus half mv initial squared plus mgh initial. Okay. So initial is 0, so you start with an initial. So you have mgh final minus mgh initial. Is that okay? So here, we're just going to do half kx. Just all the half kx final squared plus mgh final half kx initial squared plus mgh initial, okay? So here, so we're going to take, to get our k, is that okay? Let's see this here. Okay. So initially, it's not stretched. If it's not stretched initially, according to the problem, so this is 0. So I have k equals mgh initial minus mgh final times 2. Then here we'll have over x final squared. Okay. So that solves the problem. So we have the mass. The mass is given to us in the problem. So let me share the screen again to see. .596 times 9.8. So we'll do H1 minus HF is the displacement we are given, 0.170 over X final squared, or Y final squared if you like. Okay. So I'm going to stop sharing so you see what I'm doing. 0.17 squared, okay? So this is going to give us our K. So it's a conservation of energy method to solve this. Is that okay? So is this, so it's just mg H initial minus H final. So this is 2 mg H initial minus H final over X or final squared. So 2 is here, mg H initial minus H final over X final or Y final squared, which is that. So I'm going to do my calculation really quick. So this will give us 0.596 times 2 times 9.8 times 0.17 divided by 0.17 squared. 47.68. 47.68. Okay. So let's make sure we have everything right. Okay. And let me see the answer that they have here. Okay. So let's do this calculation again. 2 times 0.596 times 9.8 68.7. Sorry, I made a mistake. 68.7. I was like, what's going on? 68.7 Newton per meter. Okay, that's the correct answer for the K given in the problem. And then the next problem is for us to find the angular velocity. So square root of K over M. 68.7 over 0.596. Okay. Square root of that. 10.7. Correct, 10.7 So I'll stop sharing so you guys can see this. How I use the conservation of energy, of elastic potential energy and gravitational potential energy as the mass is dropping to solve the problem, okay? Now the next problem, I'll share my screen again. So it says, sorry, I'll make this bigger. In preparation for shooting a ball in a pinball machine, a spring constant is compressed by that. The ball is of mass. When the spring is released, which is higher than point A, find the ball speed at point B. Okay. Okay. So we're looking for the speed at point B. So we are given K, X, the mass of the ball, and goes to a higher point. Is that okay? Okay. So here we're still going to do another conservation of energy for both points. Is that okay? We're going to do another conservation of energy for both points. And then we're going to do half mv squared mgh half kx squared. Is that okay? Half mv squared plus mgh, like that. Is that okay? For both points. So let's go there. So what we're going to do here, let me stop sharing and do the equation first for VB. So we're going to do half m VA squared plus half k XA squared plus MGHA equals half MVB squared plus half KXB squared plus MGHB. So initially it started, the velocity is 0 at A. So we're going to take HB minus HA. So I'll just assume this is 0 just to keep HB as the difference. Okay. So this gives us half kxa squared equals half mvb squared plus half kxb squared plus mghb. Okay. So according to this problem, we are told that at this point B, the ball has left the spring, so we don't need half kx for B because this is for the ball. It's no longer in the spring, it's already left, so we already have this. So VB becomes half kxa squared minus mghb. Is that okay? And then divided by half m, square root of that, okay? I hope you guys can see that clearly. Okay. So it's half kx squared minus mgh of that divided by m. So the mass, the mass is going to everything. So we can put the mass in here if we like. So be half cancels half, kxa squared over m minus GHB. Yep. Uh, 2 GHB actually, because the half goes up for that part, okay? Okay, so let's put the values there. It becomes square root of the spring constant is given. I have to open the problem now. Let's share the problem now to see what's given here. Oh, sorry. $684. Let me do it on this side. I need something long. So this is square root of kx squared 684 is k. Xa squared is giving 0.067 over the mass is given 0.0585 minus 2 times 9.8 times the height difference, 0.289. Okay, let's put this in our calculator and see what we find if we get the right answer. 684.067 times 684.0585 minus 2 times 9.8 times 0.289. Um, 684 times 0.067 squared, 0.0585 minus 2 times 9.8 times. So square root of 46.8. Six point 8.5, 6.9 meters per second. Correct, as we have there. All right. We go to the next problem. It says a simple pendulum made from that height long string and a small ball attached to it. The ball is pulled to one side. How much time elapses before it attains its greatest speed? So let's find the period for a pendulum is 2 pi square root of L over G. That's problem 43. So that's 2 pi square root of, the length of the pendulum is given 1.2 over 9.8. So let's do that. 1.2 divided by 9.8 is that. Square root of that is that times 2 pi. 2.199. So 2.199 seconds is the time it takes the pendulum to start from here, go to B, and come back. The maximum speed is here, so it passes here once and comes back. So I have to divide the period by 4 to get the first part, second part, coming back 4. So it does that 4 times. So that divided by 4 will give me when it first has its maximum speed. And that gives me 0.775 meters. Sorry, let me see 1.2. Where did I see 1.2? Oh, 0.775. That's what's here. Divided by 9.8 times 2 pi. So let's redo that. Square root times 2 times 3.142. 1.77. So we are dividing 1.77 seconds by 4. 0.44 seconds. Okay, and that's the correct answer that we have there, 0.44 seconds. Okay. Okay, next problem says 1.1 kilogram object is astronauts in a distant planet set up a simple pendulum, execute makes 100 complete oscillations in that time. What is the magnitude of the acceleration due to gravity on this planet? So we have the length of the pendulum, And we can get the period. The period is 410 divided by 100. That's 4.1 seconds. So let's get G on that planet. So the period is time, total time over number of oscillations for the time. Okay. So let's do that. Looks like you guys can't see me much, so let me stop sharing. So we have 1.2 meter length and 410 seconds. So let me stop sharing. So length is 1.2 meters, 100 oscillations in 410 seconds. So the period is 410 over 100, 4.1 seconds. And that period is square root of 2 pi square root of L over G, whatever G is on that planet. So G on that planet becomes T squared 4 pi squared L over T squared. So 4 pi squared times 1.2 over 4.1 squared. That's the G on that planet, okay? 4 pi squared times 1.2 over 4.1 squared. .82. So let's check the answer. 2.82 meters per second squared is what I'm getting. Correct, 2.82 meters per second squared. That's the G on that planet. The next problem says a 1.1 kilogram object is suspended from a vertical spring whose constant is that. Find the amount by which the spring is stretched by its unstrained length. So we have K and the mass, so we're looking for X. F equals Kx. X equals F over K. mg over K. The mass is given 1.1 times 9.8 over K is given to be 110. So that's first of all going to give us the amount by which the spring is stretched from it. So let me stop so you can see what I'm doing right here. So those are the values that I'm given, okay? Mg over K, F is Kx. So let me wipe out every other thing right here. Just 1 second. Okay. So this is the A part. I know you guys can see me. So it becomes 1.1 times 9.8 over 110. So let's do that, see what we get. .0.098. 0.098 newtons. Let me check. Let's make sure we're having that right. First of all, let me share the screen and see what we get. Oh, 0.098 meters. Sorry, I'm looking for X. F over K. Okay, that makes sense. So the other part of the question is the object is then pulled straight down by an additional distance of that and released from rest. Find the speed with which the object passes through its original position on the way up. So in this problem now, we are going to do some energy conservation again for the B part. Is that okay? So we're going to get the initial elastic potential energy, half kx squared. Is that okay? The initial potential energy, half kx squared. When it's released. So the first extension we got was 0.098. Then according to the problem, it was taking an additional 0.27 meters. So we're going to add 0.27 to 0.098 to get the elastic potential energy. Half kx initial squared is half times k is given to be 110. X initial squared is 0.098 plus 0.12. The one we got before plus the additional one squared. Okay, so that's the initial elastic potential energy. And this initial elastic potential energy is going to go a long way to give the final energy at the end. So which is half mv final squared plus half kx final squared. And this x final, is that okay? It's going to be from where it started. Is that okay? Then plus mgh. So this is what we saw. So this left-hand side, I'm going to put the number here. So this is half times m. The mass is given. So I can stop sharing now so we can see what's going on. The mass is given to be 1.1 kilograms. So let me stop sharing. 1.1 times v final squared plus half times 110 times x final squared. So it passes where it started from, 0.098 squared. Plus mgh is 1.1 times 9.8 times the h. So what are we going to use as h now? So what you're going to use as h is going to be the height that it moved through at that point. Is that okay? The height that it moved through. Okay. And according to the problem here, 0.12. That's what the problem says. 0.12 meters. So let me share this to make sure I'm using the right parameters. Oh, 0.27, sorry. 0.27. So this is plus 0.27. Sorry, I kept getting it mixed up. So additional distance of 0.27 meters here, 0.27. Okay, so this solves our problem. Now we'll find V final. So let's solve that. The left-hand side, half of 110, that is 55. Then I have 0.098 plus 0.27 is that, square that, times 55. 7.45 or 448. 7.44832 equals this guy. So half of 1.1, 0.55. So 7.44832 equals 0.55 V final squared plus 0.098 squared times 55, 0.52822 plus 9.8 times 1.1, 0.27, 2.9106. So I add all this together, plus 0.52822, subtract from 7.44832. 4.0095. So 0.55 V final squared is 4.0095. So V final is 4.0095 divided by 0.55 square root. Okay. Divided by 0.55 square root of my answer. It's giving me 2.7. Oh, sorry guys, I forgot to stop sharing. 2.7 meters per second. So take a quick look. I got the initial elastic potential energy when it's released. That's the only thing that's there initially. Half kx squared, so it's additional 2.7 meters to the initial one we got before, 0.098. And then when it passes that point, so you have mgh final, it has covered 2.7 meters back to where it started. Half kx final squared, the x final squared is the extension at that point, and then half mv final squared. So we're looking for v final squared. So I just put half mv final squared, half kx final squared, mgh final. And I solve like that. And I get 2.7 meters per second. So I'm trying to check if that's the correct answer they have there when I share the screen. Of course, 2.7 meters per second. It's a long problem, but that's the way you go about it. And the last problem says a spiral staircase winds up to the top of a tower in an old castle. So we're just given the period and we are asked to get the height of the tower. So it's just the length. So period is what? 2 pi with L over G right here. So I'm just going to stop sharing. 5.4 seconds. What length corresponds to 5.4 seconds? So length becomes 4 pi squared. Length becomes gt squared over 4 pi squared. Gt squared over 4 pi squared. That's it. 9.8 times 5.4 squared over 4 pi squared. So let's do that and see what we get. $7.2 meters. I think that's exactly what we have there for the length. I'm going to share that to make sure. 7.2 meters, correct. That's the end of homework 10. I'll see you guys for homework 11. Thank you.